Hello, welcome to our course on Introduction to Cryptology. This is lecture 3 of the first week. In the previous lecture we have studied modular arithmetic, and in this lecture we will see how modular arithmetic is used in cryptology. We start with shift ciphers. Now, as we have seen in our previous lectures that in order to specify a crypto system, we have to specify few sets. These sets are the set of plain text C, the set of ciphertext K, the set of keys, and then E, the set of encryption functions which are labeled by the keys, and then D, the set of decryption functions which are again labeled by the keys. We will see how it happens in this particular example, but this 5 tuple is needed to specify a crypto system. Now, our specific crypto system, which is called shift cipher. Here P, C, K all are equal to Z by 26. So, we have studied Z sub m, that is a class of residues modulo m, and which can be written as 0, 1, 2 up to m minus 1. In this case we are taking m equal to 26 in order to associate with the letters in the English alphabet, and then so that is why we are specifying PCK as Z by 26, and here please read this m as 26. So, our K is Z by 26, which I am writing as Z by m equal to 26, and the encryption function EK is a function from P to C, which is defined by EKX equal to x plus k mod 26 for all x belonging to the plaintext set K, plaintext set P. That is the encryption function, and the decryption function is the inverse function which takes encrypted letters to decrypted to the original decrypted letters. So, that is naturally dky is equal to y minus k mod 26. So, that is the decryption. Now, we go to an example which makes this encryption and decryption clear in the case of shift ciphers. This is our example. So, this is encryption by using shift ciphers. Now, at the first step we see that we have encoded the letters into elements of Z by 26. So, Z by 26, the set of integers modulo 26, which we denote by 0, 1, 2 dot 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 up to 25, and here we see the association. A is associated to 0, B is associated to 1, C is associated to 2, D to 3, and so on. At the end x is associated to 23, y is 24, and z is 25. Now, suppose that Alice wants to send to Bob a sequence of plain text which ultimately adds up or ultimately becomes a sentence. This is the sentence: meeting time at 4. Suppose she wants to send to Bob the sentence meeting time at 4. So, she writes this. What she has to do if she is using a shift cipher is that she must agree upon a key with Bob. Let us suppose that in this particular case that key is 18. So, the key K is 18. Now, she takes these letters meeting time at 4, and first step is to encode that to numbers in z by 26. Now, so see meeting m is 12. So, here in this table we see that m is 12. So, we write 12 here, e is 4. So, we write 4 here, again e which is 4, then we have t is 19. So, we write 19 here, I is 8, we have written 8 here, then n is 13, we have written 13 here, and so on we write the whole sequence of letters. Once we do that, the next step is the key. The key gets added to each letter. So, we are writing 18, 18, 18, 18 and so on. So, in all the places we fill with 18. So, we know that we have to add 12 and 18, and that addition is going to be modulo 26. So, 12 plus 18, let us see what happens modulo 26. So, the first letter is m, which is 12, and our key is 18. So, if I add, I am going to get 30, and then I have to do 30 mod 26, which is equal to 4. The question is why? We can check this by doing usual division. So, we have let us say here we have 30, we have 26, 26, 1 is 26, the remainder is 4. So, we write 4 over here. In the case of next letter, we see that we have E. Now, E is encoded to 4, and then I add 18, then I have 22, and now if I take 22 mod 26, I get 22, because 22 is 0 times 26 plus 22. So, this is 22, and that tallies with my table over here. We have to keep on doing like this. Well, you can try it at your home, that this is to check that each letter is indeed ciphered in the way I have written down over here, and then what Alice might like to do is to shift them over again to letters in the English alphabet, and if she does that, then we will see that she is going to get something like this. 4, here it is 4, for 4 is E. So, that means M is getting transformed to E, E is getting transformed to W, because 22 is W, again we encounter E which gets transformed to W, which is 22, and so on. We keep on, she might keep write like that and send this segment to Bob, and so what Bob is getting is E W W L A F Y L A E W S L X G M J. So, Bob gets that. Now, the question is that what does Bob have to do? Now, Bob goes back to the decryption function, which is over here. Please see that this is the decryption function. So, in this particular case, the decryption function is going to be like this. So, D, the chosen k is 18, and the encrypted plain text letter is y. So, I have y minus 18, the whole thing mod 26. Now, this means that I have to replace minus 18 by something within z by 26. In order to do that, I might add 26 and then take minus 18. So, this becomes y plus 8, and of course, the whole thing has to be reduced mod 26. This also has to be reduced mod 26. So, So, we do this. So, now we have the decryption function ready for our purpose. Now, let us go to this table. Now, here Bob receives E. When Bob receives E, he changes E to 4, which is the agreed upon encoding, and then he adds 8 to 4 to obtain 12, and then see that he is obtaining the original symbol back. So, he knows the encoding. So, 12 is M. So, he knows that Alice wanted to send M to him. Similarly, he can do stepwise and get back all the letters that Alice wanted to send him. That is the shift cipher. Now, the trouble with shift cipher is that, in fact, there are many troubles with shift cipher, but one trouble with shift cipher is that it has got a small key space. So, the key space is only Z by 26. So, then there are only 26 possible keys, and therefore, an attacker can just as well check with all possible keys, and then he will get a meaningful message. For example, suppose the adversary does not know this key 18. So, what he may do is to start from 0. So, 0, 1, 2 like that, and he can do this process over and over again, and suddenly he may get, or definitely for 1 he will get this, that is 18. So, essentially if he is starting from 0, he is going to go 18 steps, 18 times he can do it, and he can do it essentially by hand. It may take a little more time. So, once he does that, he will get the message meeting time at 4. He may in some cases may get several different meaningful messages, but that probability is very small. So, if Alice is sending a reasonably large amount of plain text cipher text to Bob, an attacker it's indeed very less probable that the attacker will get 2 or more meaningful plain text when he checks with all the possible keys. So, that is shift cipher. Now, what people started thinking is that probably is there any way of extending the key space. So, because that is one of the problem in case of shift cipher, the key space is small. Well, it is possible to do that, and for that we come to affine ciphers. In the case of affine ciphers, again we have P and C both equal to Z by 26, I am sorry, Z sub 26. So, we have Z sub 26 for P and C, but the key space is different. So, let us see here, P and C both are Z sub 26, and whereas K is a subset of the Cartesian product of Z sub 26 by Z sub 26. So, we have 2 components of each coming from Z sub 26, but there is a restriction on one of the components, particularly the first component. The first component A over here has to be co-prime to 26, that is the greatest common divisor of A and 26 has to be 1. We will see why, but let us first check the encryption function. For the encryption function, we use the key A comma B, that is in the key space, and E sub A comma B is defined as a function from P to C by this E sub A B x is A x plus B whole mod 26. So, let us look at, we will look at an example very soon. Let us just have an idea of the decryption function, but for that we can try to derive the decryption function. So, what I am saying here is that E sub a b, which is the key x, is equal to a x plus b mod 26. Now, we change the notations a little. We have done this before. So, we just write like this. This is A and this is the mod 26 multiplication that we have seen in the last lecture, and then we have x plus this is mod 26 and we have b. So, this is essentially the transformation for affine ciphers, and let us suppose this ciphertext is y. Now, we would like to see the scenario where Bob has y and Bob wants to calculate x based on the fact that he knows a and b. So, he can quite legitimately do this. This is y and well this is 26 and he has to write minus b over here, modulo 26 minus b is 26 minus b. He writes this and then he multiplies both sides by the inverse of a. If he does that, then he has something like this: x is equal to a inverse y plus mod 26 minus b. In fact, this thing can be written somewhat in another way, because we have to be very careful about these things. So, if in my notation this is multiplication mod 26, but we do not have to worry that much about this. We can even write something like this, that x is equal to a inverse into y minus b mod 26. So, something that is very strictly something like this can be written in a little less strictly like this. That is not a problem. So, we have something like this. So, that is a decryption. Now, let us look at an example which will clarify the matter. So, here we take the key to be 15 and 18. Now, as we see that 15 is co-prime to 26, and there we will see that why that is useful. All right. So, here our key is 15 comma 28. So, if we want to encrypt x, then we will have something like this: E 1518 x, which is equal to 15 times x plus 18 mod 26. Now, let us try to compute the decryption function. So, the decryption function is going to be d 15 comma 28 x. This is going to be sorry, I write y here for the ciphertext, y, which is going to be 15 inverse into y minus 18 mod 26. Now, we can ask that what is 15 inverse and what is minus 18. Please refer to the previous lecture on modular arithmetic. We have here minus 18. Minus 18, strictly speaking, is not an element of z by 26. We have to map it to an element of z by 26, and we have seen how to do that. And for that, we take minus 18 mod 26, and which is 26 minus 18. This is the way to map, and so I get 8. So that is 8, that is 8 for me, and here for minus 15, for minus 15 inverse. Now we have also seen in the last lecture on modular arithmetic how to calculate inverse of an element in Z sub m if and that is possible only if that element is co-prime to m, that is its GCD with m is 1. In this case 15 has GCD 1 with 26. So, we try to do that. For that we will have to use the technique that we have studied in the last lecture. Let us do that. So, I have got 26 and I want to invert 15 here. So, 26 is equal to 15 plus 11, then 15 is equal to 11 plus 4, and then 11 is equal to 2 times 4 plus 3, and then 4 is equal to 3 plus 1, and then of course 3 is equal to 3 times 1. So, we know that 1 is the greatest common divisor between 26 and 15. We run this thing backward. So, we know that 1 is equal to 4 minus 3, and then 3 is over here. We put 3, the value of 3 here. So, 3 is 11 minus 2 into 4, which gives me 3 times 4 minus 11 is 1, of course that is true, and then we have come up to 4 again. Now we have 4 over here. So, we write 4 as 15 minus 11. So, we have got 15 minus 11 minus 11. So, this is 3 times 15 and then minus 4 times 11, and now we have to somehow write 11 in terms of 15 and 26. So, for that let us use this space. So, for that we come here, 3 times 15 minus 4 times 26 minus 15, of course, and therefore, we have got 3 times wait a moment, so it is 3 times 15 minus 4 times 26 plus 4 times 15, and that gives me 7 times 15 minus 4 times 26, and so I have 7 times 15. Well, I transpose this part to the other side. So, I have this is equal to 1 plus 4 times 26. So, I have something like this, and therefore, I can safely write that 7 multiplication modulo 26 15 is equal to 1. So, 7 is the inverse of 15 modulo 26, and that is what we get. So, if we now look at this line, it explains. So, I have to first I replace 15 inverse by 7 and 18 by 8. So, let us see. So, I have a scenario like this. So, I have well d 15 comma 12, 15 comma 18 y. I wrote that 15 inverse y minus 18 mod 26. Now, here I replace 15 inverse by 7 and then y, and this is 8. I am replacing minus 18 by 8, and so I will have this is mod 26, and then I have 7y, then I have 7 into 8 mod 26, which gives me 7y plus 56, this whole thing mod 26, and I reduce 56 mod 26, that gives me 4. So, 7y plus 4 mod 26. So, this calculation, after this calculation we get the decryption function in a quite nice way. We see that d 15 by 15 comma 18y gives me 7y plus 4, the whole thing mod 26. We can now calculate the decryption very easily. There are limitations of shift and affine ciphers. The limitations of both these ciphers are firstly that the key space is small. Another limitation is that each letter gets transformed to a specific letter when the key is fixed. That means, suppose in any one of these ciphers A is transformed to M for a particular key, then wherever in the sequence A is encountered, A is going to be encrypted to that particular letter, let us say M. Now, that is a problem, because that kind of leaks information and the adversary kind of able to is sometimes able to guess the letter, because in any language and in particular English, letters have a specific frequency of occurrence. For example, E occurs maximum number of times and then it is followed by T. So, suppose a sequence of plain text is ciphered by using a shift cipher or an affine cipher, and there is an adversary who keeps on looking at the sequence, and then he sees that a particular letter is particular ciphertext is getting repeated several times, much more many times than the other letters, then he will guess probably it is E, then fix E and then try to guess the key and or compute the key, and then he will use that key to decrypt. If he gets something meaningful, that means he is through, otherwise he will check the next possible next maximally occurring letter, and like that. So, it makes the attack much more efficient than exhaustive search. So, these are the limitations. Now, people started thinking that probably we should try to get over that limitation. So, there was a cipher which was proposed sometimes at the end of the 19th century, 1880s, and that is called Vigenere Cipher. So, that goes like this, that here we start with a positive integer m, that is an element of z superscript plus, and p, c, k all are z sub 26 to the power m. That means that they are elements of Z26 Cartesian product by itself m times. So, let me write it down over here. So, I have taken a positive integer m, and Z26 to m is simply z sub 26 cross z sub 26 cross z sub 26, this goes m times. So, in a set notation is going to be something like this, x1 dot 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 dot, and it will come to xm, where x1 comma and so on up to xm all are elements of Z26. So, we will get something like this, and so our P, C, K all are this, and the encryption goes like this. Suppose I have a stream of plain text. So, what I do is that my plain texts are now blocks of length m, and to each block I am adding mod 26 the key block k 1 up to k m. So, here the plain text will be like this: x 1, x 2 up to so on x m. Then it will be something else, x 1 plus m, let us write like this, m plus 1, x m plus 1 and so on up to x 2 m, like this. So, I have got blocks like this, and key goes like this, k 1, k 2 so on up to k m. Then I again repeat that same key, k 1, k 2 so on up to k m and so on, and the encryption is computed in this way. This one I will take x 1 subscript 26 k 1, that is x 1 plus k 1 mod 26, x 2 plus k 2 mod 26 and so on. So, this is the encrypted string, and for decryption, when I get the encrypted sequence, I will just do the inverse function, that is addition modulo 26 with minus of k 1, k 2 and like that here, and I will get the decrypted sequence. This example clarifies whatever we have discussed just now. Suppose the key is the segment crypt. So, we write c equal to 2, r equal to 17, y equal to 24, p equal to 15 and t equal to 19. Now, let us see the plain text string meeting time at 4. So, we are first of all we are encoding that to element of z by 26, and then we are putting 2, 17, 24, 15, 19 over and over again, 2, 17, 24, 15, 19, 2, 17, 24, 15, 19 like that, and then we are computing addition modulo 26, each time we get another segment and we are getting a string of letters. If we do the other way around, apply the decryption function, so then again we have this, and then we will get meeting at 4. Now, please see the speciality of Vigenere cipher. Here for example, we had E twice, once E is getting encrypted as V, and the next time E is getting encrypted as C, and for example, here T is getting encrypted as I, but somewhere down the line you might encounter T. So, here T is getting encrypted as well as 17. So, that is the speciality of this cipher. So, in today's lecture we have covered ciphers which are technically called classical ciphers. We have seen shift ciphers, affine ciphers and Vigenere ciphers. We will move on to more modern ciphers soon, but my final words here: do not underestimate classical ciphers, because modern ciphers grew out of them. We will move on to modern ciphers within a very few lectures. That is the end of lecture 3 of week 1. Thank you.